Thank you. So today we will see, yesterday we see convex integration in one dimension. So today we see all the theory of convex integration. And so convex integration, in fact, provides a tool to prove when H principle also a reduction R.
No, but they don't see it. So I mean, only you see it, I guess.
So for that convex integration, introduce in fact an explicit way. So we saw yesterday explicit deformation. So an explicit way to deform a formal solution. So here sigma to a holonomic solution V1F. And so that this homotopy is inside the section of over the relation. So for the deformation, we need an explicit formula. So here's the formula in any dimension. So we still need an initial map, F0. We need a number of corrugations, which is not zero. Data who encode the shape of corrugation. So here is a family of loop gamma, and a direction where we do corrugation. So when we do oscillation, we need to choose a direction where we want to add corrugation. So if, for example, it's just the direction of 1. And we set the following formula. So to the initial map, we add this deformation, where the amplitude is controlled by the number of corrugation, and the direction here appear in the upper bound of the integration. So we see xj here is the direction where we add corrugation, and corrugation still encoded by the loop family gamma. So then we say that F1 is obtained from F0 by a corrugation process in the direction AJ. And this, so I show you at the end yesterday, there is a lot of formula who exist to use convex integration in several cases. And why I use more this formula than each other one, because this formula has some special property. And for example, in fact, we can rewrite the previous formula without a coordinate system. So we have still F0 an initial map, so define an abstract manifold. We have n a number of corrugation. Gamma, we see that the loop family is defined following the tangent space. And here the direction, so in abstract manifold we have no longer coordinate, so we need that the direction now is given by P, a submersion. And then we could write without a coordinate system, a deformation given by the exponential map over the point F0, which had the corrugation of amplitude n/1 of still the same deformation, in fact. And of course, if we choose as parameter the initial manifold, which is 0, 1 power m, the goal space, this is the Euclidean space, and the summation, which is equal to just the projection in the direction xj, we find again the previous formula in a coordinate system. So this is just a parenthesis.
Can I have a question?
Yeah.
So in the previous slides, the family of loops only depended on one parameter, and here it depends on all of you.
So here we have still okay, right. So x, so is no longer belongs to 0, 1. So x belongs to the manifold, let's say, and we have another parameter which encodes so the one periodic parameter. So in fact, when we look at this, we have x which belongs to u. In fact, it's not more in index. That's all. So we have the parameter u, and we have the one periodic parameter. So it's like before, instead of write gamma xt, I choose to write gamma xt. X belonging to the initial space, and this is the periodic parameter. Obviously, if you want, the gamma is just defined 0, 1 type or Z.
No, I was confused because on the previous slide you had
Yeah,
from
this,
zero.
adaptation. Yeah, I understand. So, okay, so we have this formula. What are the properties of this formula? So we have still two main properties, the C0 closeness and a property on the derivative in the direction where we add corrugation. So yesterday we saw we have the C0 closeness between the initial map and the new map F1. So C0 closeness controlled by the number of corrugation. And in fact, we also have a C0 closeness between the derivative which are not in the direction of corrugation, which is also controlled by the number of corrugation. I would like to write a bit on the blackboard. I don't know if people like to write. I have to erase it. So if someone needs slides to see or no, it's what people at the end. So I just write again the formula. And I would like to take the derivative in the direction I, which is not the derivative, the direction of corrugation. So here, okay, not in the direction of corrugation. Can do d1 f1x. So ed for f0. And here, so xj, the derivative in the direction xi change nothing. So in fact, the only parameter we have to take the derivative is this one. So 1 over m0 and di. I would like to say dxi maybe. To be more precise, I take the derivative in this parameter. And in fact, I'm not really interested by the form of the derivative because I only need to know it's a loop, so in one periodic. So if I take the derivative on this parameter x, it doesn't change the fact that this is still a loop because we don't touch what's happened for s. So it's still a loop. We take the integral, it's bounded. So this, in fact, is still an error controlled by 1 over n. So that's why we have a C0 closeness between the new derivative and the previous derivative in the direction which is not the direction of corrugation. And now something happens, so then in the direction of corrugation. So now if we want to take the derivative in the direction j, we have a term coming from here. So, okay. Now if we look at this derivative, we have a new term. So we have a term coming from this derivation, and we have still this in direction j. So we have two terms, so n times 1 over n, and the value of the term inside the integral. So we take in s equals nxj. So we have gamma x. So s equals nxj minus, so here is a constant for the s, plus, as previously, this term, 1 over n, 0, nxj, the derivative on nxj, gamma x, s minus its average. This, I don't really care. It's just an error because it still loops. And here, so we take the derivative, we have a new n now. So this one vanished, and we have this part. So this part, sorry, it's a bit a mess, my results. It just saw a value on the image of the loop gamma in x and xj minus the average of the loop. And now when we assume that the average of the loop is the derivative we want to modify, that means this value vanish. So we have the new derivative in the direction dj, which equal to something in the image of gamma x plus an error controlled by the number of corrugation. It's fine for everyone? Yeah, I finished with the blackboard if you want. So now we assume that we have a formal solution where we have also a part of partial derivative. So we assume that we have a section, well, a formal solution, sorry, given by a map fj minus 1 and j minus 1 for partial derivative plus some vector field vg until a vn. And this is a formal relation of our relation, a formal solution of our relation, sorry. And we want to use the previous formula. So using a corrugation process in the direction dj. So in the direction dj, because the derivative in the direction dj is not inside the formal solution, so we want to modify in the direction dj the initial map fj minus 1. So we obtain a new map, and we have that. So we managed to obtain that for the new derivative in the direction dj. What could we do with that? So now we set a new section. So sigma j minus 1 tilde. So we keep the initial map, we keep all the partial derivative we already have, and our goal, in fact, is to replace the j by a derivative. So we want to replace the j by this derivative, so given by the loop gamma. So what is the condition such that this new section, in fact, is also a formal solution? So for that, we have to check the slice of the relation. So we define the slice of the relation in the direction dj over a point s in the relation, like the set given by all possible value we can take for the partial derivative dj, but fixing over component of the section, over component of the big tuple we have in the one which belong in the relation. So it's just a slice. What could we do for the new partial derivative dj? So in fact, so it's section sigma j, okay, j minus 1 tilde belongs to the relation if and only if the image of the loop lies inside this slice, so under the point given by fixing other component given by the partial derivative of j minus 1, or well, the other component, in fact, of the previous formal solution. So we choose this condition for the loop family gamma. So we choose a loop family gamma where the image belongs to the good slice of the relation. So now the sigma g minus 1 tilde is also a formal solution of our relation. So to build, in fact, fj, to have this derivative dj fj equal something on the image of gamma up to an error, we also require that the average of the loop equals to the derivative we want to modify, the derivative which is not in the previous formal solution. So to sum up, in fact, we have two conditions on the loop family gamma. So the image has to lie inside the slice, and its average, so the average of the loop, has to be equal to the derivative we want to modify. So in fact, the existence, like we saw yesterday, the existence of such a loop is possible if and only if the derivative we want to modify belongs to the convex hull of a path connected component of the slice of the relation. So here I talk about also path connected component. It's because I need my loop is continuous. So in fact, if I just take a slice into parts, so imagine my slice AJ. It's in fact something like that, and no, just take something simple. My slice has two path connected components. Okay, the convex hull is still that. Imagine, sorry, the derivative we want to modify. I want to modify is this one, so j minus 1. It's still in the convex hull, but when I try to draw a loop, I can't stay in the path connected component. So I need to choose gamma, but gamma needs to be continuous. So I can't continue gamma to catch it as its average. So I need to stay in the same path connected component of the relation. So that's why you have the path connected words which appear in our condition. And in fact, to obtain a H principle, the choice of the path connected component is in fact constrained by the formal solution. So for example, sorry, I have to write again on the black. So until now, I draw a relation a bit weird like it. But imagine that at one time it just collapsed to something. And there is no more convex hull, but my relation starts something else. So these two path connected components. So if I choose a formal solution here, I want to deform it, but I can't switch to the other path component for the good average here. So in fact, I have to be really careful when I choose a formal solution to be on the path component, which always contains the derivative in its convex hull. So it's really, we really need to be careful about it. Right. So now we understand a bit more the condition of the loop and the condition of the relation. And we manage, so what we manage to do, so we have a formal solution sigma j minus 1 with j minus 1 partial derivative. We build a new formal solution. So we know that it's a formal solution because the image of gamma belongs to the good set. And we didn't use yet the C0 closeness property. So the C0 closeness property on between fj minus 1, between the derivative in the direction which is not the direction of corrugation. And we also didn't use the fact we have an error there. So just as we have that, if n is large enough and if the relation is open, so if the relation is open, we could forget all this error given by a big O of 1 over n. And we know that this is also a formal solution because fj minus 1 is close to fj, so we forget the error. And the derivative, which is not in the direction of corrugation, is enough close to forget the error. And 3, gamma x is enough close to dj lj, so we could forget the error, and we still in the relation. So we managed to build, in fact, a formal solution with one more partial derivative. So the idea of convex integration, in fact, is to iterate it in the direction d1 dm to build a sequence of formal solutions. So at the beginning, we have a formal solution with no partial derivative. We start to do a corrugation in the direction 1. So we win 1 partial derivative. After we have 2, and we continue to replace all the vector field by a partial derivative. So we managed to build a section sigma m, which is the formal solution. And at the end, we obtain a holonomic solution of the partial relation given by the one jet of the function fm obtained after m iteration of the correlation process. Is it fine? It's a bit fine. So, in fact, in the iteration process, we need each time to be sure we are in the convex hull. And usually, in convex integration, to be sure we are in the convex hull, we have we ask this property on the partial differential relation. So, if we have a relation, and if the convex hull of each path-connected component of each slice of R is Rn, or if the slice is empty, then we say that the relation is ample, which is the usual assumption in convex integration. So Gromov states this theorem. So if the relation is open and ample, then the relation satisfies the full H principle. So yesterday, for example, we saw the relation of immersion for curves, and our relation was all the space except 0. We remove 0. And we see that when we take the convex hull of all the space except 0, well, it's also so the relation of immersion yesterday was ample. Still no question, it's a bit tricky maybe. Yeah, I stop with the blackboard. Thank you.
You want the other one now?
Okay. So now I will present some example where we can use convex integration. So let's go back to the relation of immersion. So the relation of immersion for map F0 from 0, 1 power m to Rn is an immersion, is an only the image of this one jet belongs to this subset of the one jet space. So that the one jet belongs to the subset given by all tuple where V1, Vm are linearly independent. So it's an immersion. So what is the slice in this case? So we fix the point which satisfies the constraints of linearly independent. The slice in the direction dy. So all the possible value, for example, for the first partial derivative, it's all possible value which not belong to the vectorial space spanned by the other vector given in the formal relation, so V2 to Vn. So that we could find a W, so that W, V2, Vm are linearly independent. So this is the slice. So let's check the slice, for example, in codimension 0. So this is surface in dimension 2. So the condition of the slice in direction 1 is all possible value for the first partial derivative is the first partial derivative does not has to not belong in the space spanned by the vector V2. So that's mean we have to find, this is the slice, so it's R2 except the line spanned by R2, spanned by V2. And we have to find a loop, gamma, such that the image of gamma belongs to the slice, so not cross RV2, and of average equal to D1 F0. And we see that it's not possible. In fact, the plane is cut in 2 parts, 2 path connected components, and each convex hull of each path connected component is not all the space. So it's up or it's down, but it's not all the space in codimension 0. So of course, if we increase one dimension, so surfaces in space of dimension 3, now the possible value for the first partial derivative, so it's R3 except a line. So now like just all the space except the line, we could turn around the line to find a loop, so which belong to, which not cross, sorry, RV2, and whose average equals to D1 L0. And we see that, in fact, R3 except a line, we take the convex hull, and it's R3 again. It's all the space. So this is ample. This is fine for this example. And so it's ample, so we could use the previous construction of convex integration. So let's, for example, consider a singular surface, the cone. So we choose a cone, okay, with this parametrization. So we have to choose a formal solution, which is in the relation of immersion. And in fact, we notice that this one partial derivative of the cone which never vanish. Okay, this one partial derivative which never vanish, we take it. So we just have to find one vector field which is linearly independent to this partial derivative, and we have our formal solution. And we need only one step here because we have to only modify one derivative. We have to only modify the second to replace V2. So we could remove the singular point of the cone in one step. So, like we see in R3 except a line, we choose an arc of cycle of average the derivative we want to modify, and we just send it on the cone. So here on the cone, we see that we only remove locally the singular point. So when we want to remove it locally, so we need a loop, of course, and to satisfy the boundary, to go back of the initial formula, we see that we retract the loop until the derivative d theta f0. So when the loop, so if the loop here is reduced to a point, it still belongs to the slice of the relation. The average is okay because the average of the point equals itself. And in fact, so yeah, I will write again on the blue. It's short. So if we check at the formula, so sorry, S and X1. So I say this is reduced to a point. So this is reduced to its average. I hope you trust me. So this is 0. Hope you trust me. And we see that, in fact, when we do contracting the loop until the derivative, we not modify the initial map. So we can glue really easily on the boundary of our surface. Is it fine for immersion? I guess I shall not. And now I would like to talk a bit about holonomic approximation again. So you saw it yesterday with Danny. And in fact, I only want to talk about the holonomic approximation for one jet space, not in every other higher order. So I just recall quickly what is holonomic approximation. So let's A, just here for the sake of clarity, A equals to little segment in R2, and we consider A open neighbor of A, and we take sigma. Okay, we just live in the jet space and define of an open neighbor of A. And holonomic approximations say there exists a way to deform A inside the open neighbor of A. So we see we deform in green A inside the open neighbor. So there exists a way to deform A, and there exists a map F1 such that on neighbor of this deformation, the one jet of F1 is as close as we want that the formal solution sigma. So this is the idea of holonomic approximation. And in fact, they exist. Sorry. So I recall the main example of holonomic approximation you saw yesterday. So usually, when we want to present the idea, we take the example of the mountain path. So we take a formal solution given by a function who go up, and asking as constraint, we want the tangent plane are horizontal. And for holonomic approximation, there exists a deformation of A's that we could go up to the mountain with a really slow slope. Sorry. So the relation, in fact, associated to this problem is all toppled such that each component are close to the formal solution sigma. And if we check the slice in the direction D1, for example, we see that, in fact, all the value, so D1 here, the slice is given by all the value such that the norm of W is really low. In fact, we want that the differential map equals 0 everywhere. So this is our condition. So this is just that here. So in fact, this is just a little ball, and it's not ample. The convexel of a little ball is not all the space. So this condition is not ample. But there exists a way to rewrite holonomic approximation for one jet as an open and ample relation. So in fact, we could solve the problem of holonomic approximation of order 1 using the previous construction. After a long rewriting, yes, but it's possible. So it means we could use the previous construction, and we could use the corrugation process here to build a path mountain as close as we want that the red function. No question? It's fine.
What about higher order?
Good question. So usually convex integration is defined for first order. I don't know if it's possible, but yeah. So I recall that holonomic approximation is for a formal solution a jet space of any order, but usually convex integration, like you see, we only change partial derivative of first order. We could change other order, but a lot of constraints. Like this. How can I see it quickly?
I didn't want to derail you. So.
No. But just to take. Usually, convex integration allow to modify this kind of derivative. So when it's homogeneous in one direction, if you have something like that, it's really tricky with corrugation, with convex integration. So usually it's possible in other order if you have a differential constraint, which look like this. And maybe I would like to say something else about it, because in one sense it's a bit surprising when we look at holonomic approximation. We have a formal solution. So sorry, I wrote L for linear map instead of the differential, and I don't write any partial derivative. So we want a one jet space, which is epsilon closed by holonomic approximation. But in fact, using convex integration, we change every time partial differential derivative. And in convex integration, there is no reason to have an epsilon closeness here. No reason in convex integration. So it's really surprising. And in fact, to manage to rewrite it like that, we just have to think that, okay, we work, we do, I would like to say, oscillation in the initial space here in holonomic approximation, when convex integration do oscillation in the target space. So to rewrite holonomic approximation like ample relation, we have to rewrite all the space and push corrugation in the target space. So the rewriting is really tricky and with a lot of computation. I can talk about it. We could talk about it later, but after it's a bit long. So okay. And I would like to talk about again one kind of example. So when we thicken some relation. So let's first consider as a toy example the following relation, where we just check where the two derivatives v1, v2 are orthogonal. We want just the angle. Why I put 0? I would like to put p over 2. I'm too tired, so okay. Imagine it's written p over 2 instead of 0 for orthogonal. Sorry. And the slice, I will draw it. So I have v1. I want to choose v2, which is orthogonal. Sorry for the typo. So my only possibility here is take v2 on a line, except 0, because I don't want my partial derivative vanish. So this is not ample because, okay, the convexel of this part is itself, the convexel of this part is itself. It's never also space. And even when I try to increase dimension, it still doesn't work. I still have a plane, except 0, and I still don't manage to catch all the space. So it's not ample. But if I thicken the relation, so forget it's written epsilon, but imagine epsilon plus p over 2. So I want orthogonal with plus or minus epsilon. And now I see that I add some freedom. So I could be not exactly orthogonal, but close to be orthogonal. So now it still doesn't work because I still have to remove 0. So okay, the convexel of this triangle is itself, the convexel of this triangle is itself. But when I increase dimension, so I have a kind of cone, really with a low slope, still remove this point, but in fact, this is still a cone, even if the slope is really low. So the convex hull of this cone will be all the space. And here we manage to have a relation which is ample. So when we thicken a relation, we manage to have something ample. And I just pick some other example in the book of Elias Berkan Mitchelchev. So for example, the relation of Lagrangian immersion is not ample, but if we add a little thickening, it's ample. The same for isotropic immersion, which become ample when we add a little thickness, but it's not work every time. So for example, still in the book, the relation of isotropic immersion is not ample, even when we add a thickening. So I guess I will change again subject. So is it fine for example previously? And I go back to immersion, in fact. So let's go back to immersion because I would like to tell you again some stuff. So we saw that the relation of immersion is ample. So we managed to remove singular point really easily for the cone, no problem. Could we do it again for a more complicated surface? So here, I take the cross cap, so representation of the projective linear plane. So what is the cross cap? The cross cap is we take the south hemisphere of the sphere and we want to glue opposite point. So we have the south hemisphere. We glue two opposite points here, and after we continue to gluing the point until close the cross cap. So we obtain that, which has two singular points. The first two opposing points we glue, and when we finish to close the surface, we have two singular points. Could we use again a corrugation process to remove it? So yes, of course, it's possible. We managed to do it. But in fact, if we look a bit closer to this surface, we only manage to remove singular points on a neighbor of the segment connecting the two singular points. So in fact, it's not localized around each singular point, it's localized around the segment connecting the two singular points. So, okay, is it then possible to localize corrugation on a neighbor of each singular point, which is a natural question. And in fact, if it's possible, we could just remove one singular point by one singular point. But this means that we have an intermediary surface closed, which is a closed curve with only one singular point. And in fact, for that, there is an obstruction from a theorem of Roussenet, which says that it's impossible. So there is, in fact, an obstruction to find a formal solution to remove one by one the singular point. And tomorrow, we will see the relation of isometric map, which is closed and not ample, but we could use a convex integration to solve it. So, I continue again. So I have the references of the talk. I don't talk about everything happening for amplitude in the literature. I add also additional references if you want, and thank you.
Are there questions for the phone?
I have a question. I'm just wondering if I'm correct about the following. It seems like one potential really cool advantage of this approach, if I understand correctly, is suppose I wanted to make beautiful pictures or movies like you have. Is it fair to say I would have an easier time explicitly numerically implementing this corrugation thing than say trying to numerically implement a proof of the holonomic approximation principle, things like that?
For holonomic approximation, I don't know, the rewriting is a bit too long, maybe for special case. Here, it's okay because first we have a finite number of steps, so because we have a finite number of partial derivatives to modify, so why not? And after, okay, the relation I solve here immersion is it's really easy to find a loop gamma. So for more tricky relation, maybe you have more problem, but this stuff I want to talk tomorrow, in fact, so maybe you could ask me tomorrow.
Thank you.